Welcome back. We made it to the last part of this chapter. So we're doing chapter 15, part D. And on this part, we're going to be talking about mechanisms and catalysis. So, what concepts are we going to cover to make sure that we understand these concepts? We're going to predict a rate law of a reaction. You already know how to do rate law. Having multiple step mechanism, given the individual steps in the mechanism. Explain the principles underlying catalysis. Before we go any further, let's make sure we understand what a mechanism is. When you go from a reaction, for example, A to that, we tend to assume until we learn about mechanism that happens on one step. Basically, A flips around. But it could be something like this. It could be A turns like this, accumulates energy, and then A turns like that. So it doesn't have to happen in one step. It happens in several discrete steps. And this is extremely important because let's say that you design a drug to combat some type of illness. And your drug goes into your proteins and enzymes and all that, and it gives you a side effect. So it's important that we can discover the mechanism of that process to understand where the problem is. And we do that by doing kinetics and study how fast the reaction goes, determining if this is the fastest step of the reaction, if this is the lowest step of the reaction. So mechanistic studies are super important. You can spend your whole life as a chemist trying to determine the mechanism of a given reaction. And it's so important that can even be an overprice, determine the mechanism of a reaction that is very important that nobody knows exactly how it works. So mechanisms, once more, are important to understand. So let's begin with this problem. So I'm gonna begin with this problem so I can explain all the concepts related to mechanism that we need to understand. Consider this two-step mechanism for the reaction. So we have a step 1 and a step 2. It tells us that the first step is the slow step, and the second step is a fast step. So a few things that we have to understand. The slow step is going to be the step that always determines the rate. It's the rate determining step. So the slow step is always the step that decides how fast the reaction is going to go. It doesn't matter that the second step happens really fast. It's going to have to wait until the first step is done. So the first step overall determines the rate of the reaction. So that's always important to know. And on a mechanism, once you determine which one is the slow step, that's the one you have to use to determine the rate law. On a mechanism, each step is what we call elementary step. And in the past, we learned that the rate law is R equals the rate constant times the concentration of the reactants to a given power. And we saw how we need to do experiments to determine that order or the power that goes with the concentration. You need to know how the rate changes with concentration, at different concentrations, and so on and so on, to be able to determine the order of the reaction. When you have elementary steps, it's a little bit different. When you have elementary steps on a mechanism, you just need to find the slow determining step or the rate determining step, which is the slow step, and you're gonna look at the reactants, and you're gonna say, okay, I'm gonna have to consider the concentration of this reactant, multiplied by the rate constant. That's gonna give me the rate. And then how we gonna find the order? The order is really easy. Since this is an elementary step, the order is nothing more than the coefficient. This is the only time when we are doing rate that we use the coefficient for the order. Once we do equilibrium, do not get that confused. It's going to be very important that you do not confuse rate with equilibrium in our next chapter. So, if we're dealing with a mechanism and you have determined which one is the slow or the rate determining step, the coefficients are going to be my order for each one of the reactants. So very simple, once you know which one is the slow step. So we just did C. We just did the predicted rate law because we found the slow step and we just used the coefficients of the reactants as my order. What is the overall reaction? What is that referring to? Well, the overall reaction is referring to the overall reaction. So we're going to combine the two steps the same way we used to do with electrolytes and so on. So we're going to see what's on the left side of the reaction, and we're going to see what's on the right side of the reaction. Anything that shows on both sides, when we combine it, gets canceled. So Cl, cancel with Cl. Make sure that the phases are the same, gas and gas. Anything that shows on the same side then gets combined. So we're going to have 2 nitrogen dioxide. So that takes care of that one and that one. Plus Cl2 gas produces 2 ClNO2 gas. And that would be my overall reaction. Identify the intermediates in the mechanism. The intermediates are going to be those species that are created on one step and then they are used on the other step. So they are products on one step and then they act as reactants on the next step. In other words, the ones that cancel. So the ones that cancel are my intermediates. We already did the predicted law by finding the slow step. And sketch an energy profile diagram. Well, that's going to be an energy profile, a graph, right? Where you're going to be doing the progression of the reaction or the time and the energy. And what do we know about this mechanism? It doesn't give us any numbers. It doesn't give us anything in terms of energy. The only thing we know is that the first step is the slow step, which means it's going to have a high activation energy when compared with the second step. So since you have two steps, you better have two humps of the mechanism, which tells you about the activation energy. Remember, activation energy, we begin with the reactants, and it goes all the way to where you see the transition state. And then the second step, you begin with the reactants, which are going to be here now, because that's where the second step begins, and it goes there. So we can obviously see that the activation energy of the first step is bigger than the second step. Therefore, the first step is the slow elementary steps. So given an energy diagram, You can tell me immediately how many steps you have. You can tell me which one is the slow by looking at the activation energy. So let's review real quick. So when dealing with mechanisms, each step is called elementary steps. The slow step is the rate determining steps, which allows you to do the rate law. Rate equals a rate constant multiplied by the reactance. In this case, there are two reactants. And since the slow step is an elementary step, the coefficients are the order. So this is overall a second order reaction. 1 plus 1 is 2. The overall reaction is nothing more than adding everything together by canceling whatever repeats on both sides. So in this case, we get this plus this, producing this. And the intermediates are what gets canceled because they do not carry all the way to the end of the reaction. They are consumed somewhere in the reaction after they have been created. And the energy profile diagram, like you know, is going to be energy versus time that the reaction takes over. You begin with the reactant somewhere. There's two mechanisms, but the first one is the slow one. So the slowest one gets the higher activation energy, followed by the second one. We do not know if this reaction is endothermic or exothermic. So this part we cannot draw it, or you have to draw it with a question mark. The problem does not give you enough information to decide if it's going to be exo or endo. You only know that there's two steps, and the first one had the higher activation energy because it's the slower one. Let's look at another example. A problem like this. Predict a rate law for a reaction that have two mechanisms. The reaction shown here, this one, for which these are the mechanisms, is experimentally observed to be second order in X and first order in Y. So it's telling us that the rate is going to be given by a rate constant multiplied by the reactance. And it's telling us that it's second order in X and first order in Y. So the overall order is third order. But this would be the rate law. So this would be the predicted rate law according to this statement. So which question do we have? What is the overall reaction? The overall reaction is putting all of them together. So X2 gets canceled. One of the X's get canceled. And overall, we get X plus Y produce XY. And we better get that because it told us that this was the reaction, right? So that agrees with the first statement. The overall reaction, the one that comes out of the elementary steps, had to be the one they gave us because it was already given. So we got the overall reaction. Identify the intermediates. The intermediates are going to be X. That would be one of the intermediates. And can we say that X is an intermediate? No, we cannot say that because we end up with X. It doesn't get consumed. What is the predicted rate law? We already got the predicted rate law. But there's a problem. Based on what you learned so far, the slow step had to give us the rate law, right? And I told you, really easy. Identify the slow step and then do the rate law. rate equals K times the reactance of the elementary step that is the slow step using the coefficients, right? Do you see where the problem is? We got a huge problem. It told us that we know the rate law experimentally, right? We know the rate law, which is this one here. And the rule is that if you find the slow step on the mechanism, you should be able to write the rate law really easy, and it's not matching. There is a problem. This should match, and it's not matching. Guess what? There's another concept that we have to discuss. So if we go back to the first one we did, I want you to notice this. On the first one we did, step number 1 was the slow one. On this one, step number 2 is the slow one. And that is going to create a problem. Imagine you going on the highway, and then you get out of the highway and you go into a one-lane street, and you come out of the highway, you're gonna make it home, you traveling 60 miles per hour, you're not violating the speed limit, but right in front of you, somebody comes out of the driveway and they're driving at 5 miles per hour. So you're going really fast, but in front of you, there's somebody going really, really slow. And there's nothing you can do. So the best thing you can do probably while driving, start talking on the phone, reach equilibrium so you don't have a heart attack, right? So that's the same thing is happening here. The first reaction is really fast, but then it gets behind a very slow one. So what happens, this reaction, by the time the slow one is done, this reaction have reached equilibrium. And we denote equilibrium by doing 2 arrows. So it's going back and forward, back and forward, back and forward, waiting for the slow one to finish. So when that happens, then the rate law becomes complicated. We're actually going to call this the steady state approach to determine the rate law when you have a reaction where the first step is not the slow one. So we're going to say that there's a rate constant going forward, K1, and there's a rate constant going backwards, K2. And they have reached equilibrium, so the rate going forward equals the rate going backwards. So the rate 1, which is going forward, is going to equal the rate 2, which is going backwards. And you know how to write rate. Rate 1 equals rate constant 1 times x to the square. Remember, this is an elementary step, so we're going to use the coefficient as the order. And we are saying that that rate, so rate equals that, right? So we know that. We are saying that that rate equals the rate going backwards, which is going to be K2 times that to the first order. I'm just going to put it there so you can see it. So that's what we have. So why do we need to do that? Well, we need to do that because we know the rate law, according to the slow step, is K3, this K3 there, right? Times the concentration to the first order times the concentration to the first order. But the problem with that one was that X2 was an intermediate. So you cannot have intermediates on the rate law because they're going to get consumed. So what we're going to do then is express that intermediate with other concentrations. So given this equilibrium, we're going to say that K1 X2 over K2 equals X2. So this is us expressing our intermediate, right, as something else. So what we're going to do now, we're going to take this expression and we're going to put it there. So let's rewrite this. So instead of putting the intermediate, now we're going to put K1 X squared over K2, which used to be my X2 there, to the coefficient of 1, multiplied by Y. So that's my rate order. Yeah, but that doesn't look like this yet, right? So I thought we did all that so it will match, because it had to be like that. Well, this is what we're going to do. We're going to take this number, and this number, and we're going to combine them mathematically. So K3 times K1 over K2. So rate is going to be K3 times K1 over K2, all that multiplied by X to the square times Y. So in other words, these three numbers combine to my K. It's just a number, right? X squared Y. Does this looks like that? And the answer is yes. So this is how you approach a problem where the first step is not the slow step. And it's because an equilibrium is established, and when you do the slow step, when you use the slow step to do the rate law as I showed you, using the coefficients as the powers, you end up with an intermediate. You cannot have an intermediate on the rate law. So by using the steady state approach, you can get rid of that intermediate and get an expression that helps you solve this problem. So if you need to stop this, rewind several times back and forward. That would be a lot more effective than me repeating this again. And check the textbook. The textbook have an excellent example, step by step, on how this is done. So this is the steady state approach approximation. This is the type of problem that if you're taking like the NCAT for the chemistry section or something like that, this problem will show there, because it's one of the ones they consider difficult ones, which is not really difficult if you keep track of what you're doing. So review this as much as possible. Let me know during the workshop if we had to go over this. And here's your daily work. So let's do some more learning. So we have this reaction now. And it was taken to the lab. We did experiments, and holding chlorine constant, we came up with this graph. So we're only looking, we held chlorine constant, so we're only looking at nitrogen monoxide. And what can we see right away? We are plotting the reciprocal versus the time. And if you remember when we studied the integrated rate laws, that means that we're checking to see if this is second order or not. If it was zero order, we would be just plotting the concentration versus the time. If we were checking for first order, we would be plotting the natural logarithm of the concentration versus time. So in here, we're checking to see if it's second order. If it's second order, we should get a straight line. And that's exactly what we have. We have a straight line. So we know that on the rate law, when you do the rate law for this reaction, right? You're going to have your K, and you're going to have your NO, and it's going to be second order. It's second order because the information is telling us that, the experiment, not because of this coefficient, because this is the overall reaction. This is not an elementary step. So we're not using the coefficient unless it's an elementary step. But from the graph, from the experiment, we know it's second order. And tentative, we're also going to include this here. And I say tentative because sometimes when you do your experiments, you notice that some of the reactants are not included on the rate law because it could be zero order in respect to that one, right? And if this is zero order, then this is just a 1. So sometimes you don't see all the reactants because they can be zero order in respect to that. But we don't know yet. So we're gonna keep it there, and we don't know the order. If we look at the overall reaction, which is the one given here. However, we are given a mechanism. And immediately you notice, this is one of them. This is one where the first step is not the slow one. So I'm gonna have to do a steady state approximation. But don't rush that much, because this problem is not asking you to do that. In the following mechanism, is the following mechanism consistent with the data? Well, according to this, we have 2 steps. The first thing we have to see if the overall reaction comes out of the mechanism. So let's add the 2 reactions together. NOCl2 cancels. The NO gas on the left side combines to give us 2 of them, plus Cl2 gas, producing 2 NOCl gas. So the overall reaction from the elementary steps matches the one that was given. So step 1, we took care of that. So it matches, so no problem there. But that's not the question. The question is, does it matches with the data? The data tell us that is second order. What the data is telling us is that it's second order in respect to nitrogen monoxide. So how can we double check that? Well, we're going to have to do a steady state approximation. This is my slow step. Therefore, my rate law, which is always based on the slow step, is going to be K times the concentration of the reactants to the coefficient, and O to the coefficient. So that's the rate law that comes out of the elementary step, which is the slow step. However, as you already saw, that is an intermediate, which means it cannot be in the reaction. So we're going to take advantage of the steady state approximation that tells us that the fast step before the low step is going to have to wait, and what is waiting is going to establish an equilibrium. And we're going to say that this is K1 going backwards, and K2 is going forward. Doesn't matter, that's just a label. So we're going to say that R1 is going to be equal to this, which is going from right to left, K1, times NOCl2, right? And it's going to be to the power of 1 because this is an elementary step, so we can use the coefficient for that. Meanwhile, R2 is going to be K2 times NO to the power of 1 times chlorine to the power of 1. And since they have reached equilibrium, K1 times NOCl2 is going to equals R2, which is K2 NOCl2. And we're doing the steady state approximation because we need to get rid of this intermediate, NOCl2. So what we're going to do is NOCl2 equals K2 over K1 times NO times Cl2. So with that given, now we can take this, which is going to be this over here, and put it there. So let's do that. We're going to do the K that we originally have, K2 over K1, and O times Cl2 times NO1. So when we do that, what do we have? You're going to have R, the rate, is going to equals all the K's combines. So a new K, the NO gets squared, and the Cl2 goes there. Does this match that in there? The data told us that it was second order in respect to nitrogen monoxide, and that's exactly what we have. Second order in respect to nitrogen monoxide. And it's also telling us that the chlorine is going to be first order. Does the linear plot guarantee that the overall rate law is second order? No, it doesn't. The overall rate law is third order. So remember, the linear plot that we did was because we were holding Cl2 constant. So we haven't done the experiment to figure out Cl2 at that time. So that plot by itself doesn't guarantee that the overall reaction is second order. In our case, the overall reaction is third order. Second order on nitrogen monoxide and first order on chlorine. And we use once more the steady state approximation because the slow step wasn't the first step. And with that, I would say that we know how to predict a rate law now when we have a multi-step mechanism. As long as we're giving each steps and we're giving the information about which one is the fast one, which one is the slow one, because we're looking for the slow one. And when you do the rate law based on the elementary steps, the order is the coefficient of those reactants. And if you end up with a reactant that is an intermediate, then you need to use the steady state approximation to express it without showing the intermediate, by taking advantage that the fast step before the slow step is going to reach the equilibrium, and you can equal the rate going forward to the rate going backwards and mathematically take care of the intermediate. So the last objective we have is talking about catalysis. And this is what I'm gonna show you about what catalysis is. And you probably know this from biology, right? You have a container and you wanna put that circle inside the container. So how can we do that? I can leave those two on the screen and start thinking really hard with my mind until the ball gets inside the container. That will never happen. However, I can use the tools that I have, and I can take that, I can copy it, and then I can put it there. So I was able to use a tool to get what I want. So that's what a catalyst is. A catalyst takes a reaction that is happening one way, and that catalyst, which is a tool, allows us to carry that reaction on a different way. The classic example is the enzymes in your body. Your enzymes are gonna, for those of you that have taken biology already, your enzymes are gonna have the primary structure, the secondary structure, then it's gonna start folding, and when the enzyme folds, it creates the active site. Those active sites, that's where the reactions are gonna happen. So this enzyme goes and gets reactant A, gets reactant B, puts them then together into the active site, and the reaction takes place. Very similar to what I just did on the screen. So all the energy that was required for those two reactants to come together now has been minimized because the enzyme is helping, or because we're using a tool. So in terms of reaction mechanism and rate, a catalyst, what it does is it reduces the activation energy. So that's all we're going for here. The main concept is a catalyst allows a different pathway, and in the process reduces the activation energy. So let's do this problem. Consider this three-step mechanism for a reaction. This is one of those where the slow step is not the first one. So if you want to do the rate law, you're going to have to do the steady state approximation. So let's see what the problem is asking. Sketch an energy profile diagram. So I'm going to have my y-axis. I'm going to have my x-axis. The y-axis is energy. The x-axis is time. That's the reaction progress. How do I do an energy profile for something like this? Well, 1, 2, and 3. 3 steps. So I'm going to have 3 humps. The second one is the slowest one. First one and third one, the only thing I know is that they're fast. I don't know how fast they are in relation to each other. I know they are faster than my second one. So the best thing I can do with this will be something like this. And I really don't know if it's going to be exo or endo, so I cannot tell you that. But from here to here, that's one activation energy. Remember, these are the reactants now. From here to there, that's another activation energy. And from here to there, that's my other activation energy. It's obvious that this one is the higher one, which means the second step is the slowest step, which is what I'm saying here. The second step is the slowest step. So that's the best energy profile diagram I can give you without any other data. Sketch it again, showing a catalyst in action. So if I'm going to show a catalyst, what I need to concentrate on is on the fact that the activation energy of the slowest step, the one that determines the rate of the reaction, is going to be slow. So if I'm going to show you if I'm going to show you how this looks with a catalyst, I can do this. I can keep that the way it is, and then make that one smaller, and I can keep that one the way it is. It could be that step 1 and step 3 also go down, but I don't know. The only thing I know for sure is that the rate determining step, the slow step, is gonna go down in activation energy. So that would be a good representation of this reaction with a catalyst. So every student can do it differently as long as you show me that the slow determining step, the one with the higher activation energy, see a reduction on the activation energy. And that's your daily work. And with that, we come to an end. So on this last recording, we saw how to predict the rate law for a multi-step mechanism. We saw what an elementary step is. We saw that the slow elementary step is the rate determining step, the one where you can get the rate law from. And we saw that the orders of the reactants on the rate law is the same as the coefficient only for an elementary step in a mechanism. And now we understand what the catalysis is. So quick review. So what factors affect the rate of a reaction? Temperature is the main one. We know how to relate the disappearance of the products to the appearance of the reactants to the rate, right? The change in concentration of one of the reactants by the change in time give us the rate. And it's going to be negative because the reactant is being consumed. If you do it in relation to the product, then it's positive because it's being created. And if we have a balance equation, each of those expressions, change in concentration over change of time, has to be divided by the coefficient. That way, you have a proportion between all of them, because it doesn't matter if you do it with the reactants, with any of the reactants or with any of the products, the rate has to be the same. And we saw how to determine the average rate, which is what I just told you. And the instantaneous rate, you need a graph, and then you need to do the tangent to that particular time, and then you do the slope. We talk about how to write the rate law, how to write the integrated law. We saw how we can use the integrated law to do predictions of how much remains, how long it takes, which we became familiar with the half-life. Now we just talk about activation energies. We did it earlier when we were trying to do understanding activation energy and using the Arrhenius equation. And you know that the Arrhenius equation looks like a straight line, or you can have the two temperatures format also. And now we talk about mechanisms and catalysis. And with that, we have come to the end of chapter 15. So once more, take notes. Anything that you would like to go over again, make sure you bring it to the workshop. Even better, send me an email so I can come prepared to answer those questions. So until the next time, see you later. Take care. Next thing is chapter 16.